Hello?
Okay, let us start. Let us start. Okay, last week we basically have to memorize the shape, right? It doesn't mean they cannot draw this way. Usually textbook will tend to draw it this way. You need to remember the velocity displacement graph, acceleration displacement graph. That's the acceleration displacement graph. Memorize the formula. This formula also remember that. Right? Don't need to know about eclipse, all that, even though it's eclipse. Then after that, you need to remember your sign graph for displacement. Right? That sign graph there, that's your sign graph for displacement. Then if you can remember the other graph, go ahead. If not, know how to differentiate. Right? That is the equation for you to know. Right? For this blue graph, then differentiate to get the velocity. Right? And then you can roughly draw the graph. And after that, acceleration is always opposite to it. It's the same except there's a negative sign there. That's all. Right? You can see that there's a red, the blue one for displacement. That's the acceleration. Always opposed to your displacement. That's all. Easy to remember. Right? Velocity is leading by 90 degrees. That's all. Easy to remember. So let us solve one problem. Right? We have done all that. Right? This is an A-level question. Right? They will ask you define. That's the first mark you have to receive. I can remember. Well, how to define. Yep. How to define simple harmonic motion. Can? Forgotten already. That's why I say if you don't review what I teach you, you have forgotten already. Right? Acceleration is proportional displacement from a fixed point and always directed towards a fixed point. Okay. This is a worksheet that I've given you. You have downloaded it, you should be able to follow number 9. A tube sealed at one end has a total mass M and uniform cross-sectional area. Uniform cross-sectional area is just below here. Below here. The tube floats upright in a liquid of density, right? Density of liquid is given, rho, and length of the part there below water is L, submerged as shown in diagram. The tube is displaced vertically and then released. The tube oscillates vertically in the liquid. At one time, the displacement is shown in the figure 3.1b. This is 3.1b. Right? You displace it, you push it down by a distance x. Theory shows that, right? This one they didn't expect you to derive, but you are expected to derive. A-level students, they don't need to derive. They will be given this equation that is derived for them. Explain how it can be deduced from the expression that the tube is moving with simple harmonic motion. How do you think I should solve this question? Okay, given the equation, how do you know it's simple harmonic motion? You just define it. Yep. Any idea? Yeah, from the equation itself there. A is constant, rho is constant, G is constant, M is constant. So A is proportional to X. Negative sign shows that The two are always opposed to each other. That's all you need to explain to them. Okay.
The A and X are opposed to each other.
Negative sign shows that A and X are opposed to each other. That's all. Can?
Can.
The tube of cross-sectional area given is floating in the water of density given. Calculate the mass of the tube, which should give rise to oscillation of frequency 15 Hertz. Right? Compare this one. This is the equation that they derive for you. You don't need to derive. Okay, compare with your definition. That's the definition. So this is omega square, this one. Right? The X and the A is there. A and X is there. Negative is there. So this is your omega square. And omega is 2 pi F. Okay. Put your value in for omega, 2 pi F. AG, A rho GM. Then calculate your, you want to calculate the mass, that one there. Cross multiply, put in your value. Right? Or put in the value 2 pi F. F is 1.5. A, oh, I'm a bit careless here. Should be 4.5, I write 4.4. Right? cm convert it to meter square. Let me just carelessness. And then density is there. Write down there. G is 9.81. That's your M. And then go and calculate your M. Okay. You can put kilogram if you want to. Any comment? We will derive some equation for spring and simple harmonic motion using this idea later on. Okay, any question? Can I go to the next slide? Anything that's not clear?
No, all okay.
Okay, as I said, circular motion is also like simple harmonic motion. The radius of this ball, radius or the distance of this ball from the center is the amplitude, that's all. We can show it in a dark room where you can shine light there, and then you can use photographic strip that's moving, right? Convert the circular motion to sinusoidal, right? But it's not required anymore. My time we have to study all this. Your time is not mentioned in your syllabus, but your reference book, just go over that. If you want, can read that yourself. Okay. Right, for info only. Same right here. Right? You can shine light there. There's a screen doing the dark room there. And you look at the ball there. Right? As the turntable move in circular motion, the ball there, the shadow of the ball, move in simple harmonic motion. Okay. Angular frequency equals to angular velocity, that's all. Right? Angular velocity of the ball equals angular frequency of the oscillation here. Right? That's why I show you. Can get it from internet. Okay, let's go to 19.3. Energy in simple harmonic motion. Right? Page 10 in your book. If you want, you can refer there. Right? We are interested to derive and use the expression for kinetic energy and potential energy. Describe the graphical illustration, the variation of kinetic energy and potential energy with time and displacement. Okay. We want how the potential energy and kinetic energy and total energy varies with time and how it varies with displacement. Okay, energy in simple harmonic motion. In simple harmonic motion, okay, remember they call it total energy of the system. System is simple harmonic motion, not the total energy of everything. Keep that in mind. That means it's total energy or total mechanical energy of the motion. In simple harmonic motion, no energy is lost to other form as there is no resistive force. Remember, we are doing the experiment in a vacuum, no resistive force. So the oscillation will go on forever. keep on going. Okay, of course, there's no such thing now, but that is the perfect simple harmonic motion that we are looking at. As the particle oscillates, the kinetic energy is transformed to potential energy and vice versa, right? Just like simple pendulum, right? It goes from if it's at the maximum displacement or amplitude, maximum potential decrease, kinetic increase to rest position, kinetic energy is maximum. Then after that, swing to the other part, where the potential energy start to increase, kinetic start to decrease until maximum kinetic potential energy. Kinetic energy is zero. Then keep on going. Okay, for spring, you go up and down. Okay, but in this case, the potential energy is elastic potential energy. Right? So when we say total energy, it's total energy of the system. Right? So the total energy of the system is constant at any time. Right? Or we can write kinetic to potential or kinetic to potential. Right? Whichever symbol you prefer. Okay? Energy is simple harmonic motion. We can have two springs there. Right? One of the questions is there. You can try it out. Right? We can represent the spring, the two spring as the intermolecular force, the trolley as the ions. Right? So it oscillates. We can think of it as this is the atom oscillating or the ion oscillating in the solid or in the liquid there. Right? That's how we model what we cannot see with what we can see. Okay, so in this case, it's normal gravitation, it's elastic potential energy, no gravitational potential energy. Okay, let's go back. Page 10, number 2. Right? Go back to this equation for velocity at any displacement. Right? Velocity at any displacement. That's the velocity at any displacement. Right? Remember the kinetic energy is zero here. Right? Think of a simple pendulum. That's the best way to think of it. And then potential energy is maximum. And at this part there, kinetic energy is maximum, potential energy is zero. Okay. So you want kinetic energy, right? Square that, right? Square that, and then place it into the formula. Right? Omega square, and then square that one becomes x naught square minus x square. Then we know how to interpret. Right? Open it up, remove the bracket, expand it. So this is your total energy. This is the maximum kinetic energy or the total energy. This must be potential energy. Okay, total energy minus potential energy. Okay, so this is any total energy of the system or total mechanical energy. Mechanical means potential and kinetic. But usually textbook won't use mechanical. It's understood when you say total energy means total mechanical energy. Right? It's the potential energy. The best way to remember is like a spring that you study in your SPM. R K X squared. If it's a spring, your K is your elastic constant. Right? Or your spring constant. In this case, your K is M omega squared. Right? It's a constant of the system. Stop me if I'm going too fast. Okay, so this total energy is also maximum kinetic energy, is also maximum potential energy. Okay, so remember, this is energy stored in spring. Easy to remember. Usually we work with potential energy easier rather than go and try to work this equation out. You can if you want to, your choice. Okay, so how does the graph look like? As I say, you can look at here, right? The table that I teach you how to derive, which is easy. Use your what you have knowledge in your SPM and then draw the graph. Okay, or look at the equation that's on page 11, number 7 in your book there. Right? Potential energy is a parabola. Okay, so it looks that way. Right? Remember, your amplitude must be there. And total energy is the largest value where it touches the amplitude. Draw a horizontal line. That's the horizontal line. Total energy, E right? And then you can go, your total energy is kinetic plus potential. For kinetic, take the potential across equals minus EP, E minus EP. So it's just upside down, that's all. Inverted, that's all. Okay, that's all. Right? So that is your kinetic energy, this one. This is the total energy. This is the potential energy. Easy to remember potential energy. I can draw the total energy. Right? Remember, it cannot go outside because that is the amplitude. That's the amplitude. Okay, then you can look at for any displacement, draw a line. It can be anywhere around here. I must be able to read the graph. That height there is potential energy of the particle at that displacement, EP. Right? And that one there, reading this curve there, is the kinetic energy of the particle at the same time, at the same displacement, that red line there. At that displacement, at that particular displacement, that's the potential energy, that's the kinetic energy. But you must also remember, right, that part is your potential energy, equivalent to this part. Right? Or this part, that red part there, from here to here, is the kinetic energy. Should be able to read that. Right? Because you are just using this formula. Hours. Okay. Any question? Anything not clear? If okay, let's go. Right? Now we have looked at how the energy changes with displacement. Now let's look at how the energy changes with time. Okay. Just neglect this part. Just neglect the other part if you want to. Oh, that is your period there. Right? You have to sketch. Right? You have to sketch. This is your x naught. This is your minus x naught. Sorry, slightly out. Right? And then we go to our equation. That's our equation for your simple harmonic motion starting from the rest position. That's the oscillator. Where x naught is the amplitude, omega is the angular frequency. Right? This is an oscillator starting from rest. You must be able to recognize that. That formula means it starts from rest position, moving to the right. Right? Amplitude is constant, remember, simple harmonic motion, no friction, no air resistance. Energy, right? If you think of potential energy, you can write m omega square if you want to. Right? Intentionally write this one to help you remember your elastic potential energy in your spring, energy stored in spring. Right? Square this one, put to the equation. Okay, or A-level student, they don't need to go over that. They just need to know you square this one, you get this one. And then you square this one, you get that one there. Right? You square this one, it becomes all positive. Okay, as I show you, it's still sinusoidal. Right? You don't need to know that far, but it's still sinusoidal, not sharp there. Sinusoidal. Period. Right? This is the period of the oscillate of the displacement. So the period for the energy graph, potential energy graph is this one, T over 2. Okay. So here I'm just redraw for you. There's a displacement time graph. This is the potential energy time graph. Right? Total energy is constant. Total energy equals to maximum kinetic or maximum potential energy. Right? Just and then the potential energy at any time is given by this formula. Right? Or you want to square properly, you can square properly. That's the equation. Right? So that's the total energy. And then just remember, The kinetic energy is inverted, right? Just different from potential energy. Potential energy, that's all. Where this is zero is maximum. Where this maximum is zero, that's all. That way, it's all in your book, page 11 and 12. Any comment? Right? Just remember your displacement time graph, then draw your potential energy. You just square that one there, that's all. Right? So that's your displacement time graph. Square this becomes that, and then square the negative becomes positive. That's all. It's still sinusoidal, no sharp point there. Right? Still a sine graph, or we call it sinusoidal graph. Okay, any comment? And after that, you can get your total energy. Total energy is at the maximum there. And after that, you can get your kinetic energy. Okay. Right? You can draw it this way. It's up to the individual. Some of them prefer your potential energy at zero first. So it depends on where you start. Right? Mine, I start with differently. I start with potential energy zero. I use my sine graph. Okay, or if you have a spring and a mass there, right? Basically the total energy is constant. So when it move up and down, it's changing the kinetic, gravitational, and elastic potential energy. Right? This gravitational potential energy, this elastic potential energy, that's all. Okay, so we have completed this part. Let's try some question. Okay, so we have completed all this part. We still got this part there, 19.5, 19.6. So when you want the next class, you let me know. And any idea where you want the next class, next hour? Okay, let's go to your worksheet. That I've asked you to download. I hope you have downloaded it. If not, you're not going to learn anything. Define equation for simple harmonic motion. Identify the symbol. What is A? What is A?
Acceleration.
Omega? Omega?
Angular frequency.
X?
Displacement.
Okay, good. State the significance of the negative sign in the equation. Why you have this negative?
To show that the acceleration and displacement are opposite signs.
Not opposite sign, in opposite direction.
Opposite direction. Okay.
They always oppose each other. That's the idea.
Oppose. Yeah.
Acceleration and displacement always oppose each other. Or another way of saying is always 180 degrees out of phase. Okay. This one is in your reference book. I didn't derive for you, but we will be doing part of it the next lesson. Frictionless trolley. Right? That's your trolley. Our mass M is held on a horizontal surface by means of two similar springs, each of spring constant K, each of them is K. The springs are attached to a fixed point as illustrated in figure 2.1. When the trolley is in equilibrium, this is where it's not moving, it's stationary, the extension is E. Right? Where this is the extension E, if you draw the graph for this part there, right? There's your E there. Right? The rest position, you can think of this is your displacement, if you like. This is your displacement. The trolley is then displaced a small distance x from the right along the axis of the spring. Both springs remain extended. Right? Remember, the spring is already stretched. The extension is E. Right? Extension is E. Then you displace it to a distance x. Right? So it's now become E plus x. Okay. So let's review that. Right? This one becomes longer, F1, E plus X, because F1, right? That is a left spring. The right spring, so the force F1 is just K, extension is E plus X. Right spring, there's the initial position. Right? You are stretching it by X there. Right? Remember, you are shortening the spring. Right? Shortening the spring. So it's E minus X. This one, you are making it longer. This one, you are shortening the spring. The spring is here. You have to imagine that. Right? That's what is happening. You are shortening the spring from E. You're shortening it by X. This one, you are increasing it by X. This one, make it longer. This one, is shortening it. So F2. So the resultant force, right? Resultant force is your F1, which is larger, minus F2. Right? This one minus that. So you simplify that, becomes your KE minus KE, 0. So KX minus become plus is 2KX, and the force is to the left. Remember that? It's a vector, so you must tell the position to the left. Okay. Any comment? Okay, the trolley is then released. Show that the acceleration A of the trolley is given by the equation. This one. So you should be able to show. Right? Resultant force, that's the Newton's second law. Okay, we already got the resultant force is there. MA. Right? Remember the force and the displacement. The displacement is to the right, positive. The force is to the left, negative. That's why you put a negative sign there. Right? A and displacement, negative sign there. So now we want our acceleration. Take our M down, take a negative sign across there. So we got that equation. That's what we are supposed to show. Okay. So after they show that, they will have to use the equation, compare with the standard equation. The mass M of the trolley is 900 grams, and the spring constant is K given. By comparing your answer in A1 and your equation in A2, right? Your definition and this equation, determine the frequency. That's all. Compare. That's your definition. That's what we have derived. So your, right, take the X down. 2km equals omega square. Then we take square root that. Remember your 2 pi, omega is 2 pi f. Okay, take the 2 pi down. Omega over 2 pi. And take this one down there. And put in your value and calculate out. Right? Suggest why the trolley in B provides a simple model of the motion of an atom in the crystal. Right? The trolley can represent, as I say, an atom or ion. The two fixed point can also represent your other two atoms. The string can represent your intermolecular force or your bond, right? Your elastic bond. That's all. Okay. Any comment? If not, I will stop here. Anything else you want to ask? Make sure you try the worksheet and 19.3.
No, sir, nothing so far.
So I'm doing very small topic for you. Give you a chance to try it out, to force it in. So spend another hour going over it, review the topic. Okay, I'll stop here. You got no question to ask? We will stop here.
Okay, thank you, sir.
Okay, bye-bye.